Hey everybody, thanks for tuning in. I'm Zach Peterson. I'm a technical consultant with Altium, and today we're going to continue talking a little bit about differential pairs and specifically why you need to length match your differential pairs so that you can properly read out signals in an interconnect. When you have a differential pair, it's composed of two traces, and those traces need to be routed with the same length. So how exactly do you do this if you need to make a lot of corners, go through vias, stuff like this? We're going to look at that today. So let's get started. I'm just going to draw out top view of a layout, and we've got our differential pairs. Let's say they're routed at some angle like this. So here's one of my differential pairs, and then here's another differential pair. And they're being routed over to a component here on some side of the board. The reason that you need to take these differential pairs, or each side of the differential pair I should say, and make these traces the same length is so that you can properly read out the signal at the same time on each side of the differential pair. So let's look at the graph of the signal just to kind of clear this up. So here on my positive side, I have a signal that looks something like this, okay? So let's just say it looks like that. And again, let's just say that this is like 1 volt. Now on my negative side, we have an equal and opposite signal. Okay, so ideally they have the exact same shape. Ideally this is also at equal and opposite voltage, so -1 volt. In the ideal case, this edge, this rising edge of the positive signal, and this falling edge, or it's a rising edge just in the opposite direction, of the negative signal happen at the exact same time. So what that means is that when the signal arrives right here on the interconnect, these two signals are changing and then reach their final voltage at the exact same instant in time as they reach the receiving component. That will ensure that at this point in time and the corresponding point in time on the other end of the differential pair, the difference between these two signals is going to read out to essentially be double whatever your positive signal is, or double whatever your negative signal is, depending on what polarity you want to define. This is one of the reasons that we need to have the two sides of the pair length matched. When the two sides of the pair are length matched, these signals are traveling at the same velocity, and if they have to travel over the same length, they're going to arrive at exactly the same time at the receiving component. So just to see what happens if you don't have that enforced, let's just ask the question. What would happen if my positive pair, P, and my negative pair, or my negative side of the pair, N, have different lengths? Well, if they have different lengths, but they travel at the same speed, then one of the signals, so let's say the pair on the signal on the positive side, is going to arrive at a different time than the signal on the other side of the pair. So let's just say for a moment that this is the shorter length, and then this is our longer side of the pair. So if these two have different lengths, here let's just say at t equals 0, right here at this instant on at the receiver, the positive side has a signal that starts rising. Now if the negative side is longer, then the signal is going to be delayed. Now what happens is if it's delayed a little bit, here they don't line up, and you only have a match between the two signals in this small interval in time. So the voltage that you need to induce a digital signal or a digital logic state in the receiving component only exists within this time period. And so you'd only have 2 volts measured between these two traces right here in this time window. If the two don't overlap, you may not read out the digital state correctly at the receiving component. Now there's another reason for this, that we need to have the two length matched. And I mean, yes, reading out the digital logic state that's being transmitted over this pair of traces is important, but there's another reason, and that relates to being able to cancel noise from the interconnect. Let's just say for a moment that way back in the beginning of this signal's life, when it was sent from a receiver or from a transmitting component at the beginning of this interconnect, there was a little bit of a noise that was induced on this signal as it rose. So let's just say on the positive signal, it started right here, and there's some bit of noise. And on the negative signal, we also had that same issue back here at the transmitter, and we have that same noise. So this is all common mode noise. Well, now if one of these signals, or one side of the signal, I should say, is delayed on this transition between the transmitter and then the receiving component, you now have a mismatch between the timing of these two noises. So if there's any mismatch between the timing of these two noises, when I then take the voltage on the positive side minus the voltage on the negative side to read out the signal, you'll notice that I need to subtract out these two noises in time. But because they don't overlap, they don't actually get subtracted. So this is the other reason that you need to make sure that the lengths of your differential pairs are matched. It's to make sure that if there is any noise received anywhere else on the interconnect, that the noise is coincident on both sides of the pair at the exact same time at this receiving component. And that's what's going to allow the receiver to cancel out this common mode noise and eliminate it from the signal that it actually needs to measure. In order to do this, let's say that this trace is longer than this trace. Well, then what we need to do is we need to lengthen this trace a little bit. So we need to increase its length. And so if you watch the previous video, you'll see that I showed this little tiny structure that gets added in order to match the length of these two pairs. And sometimes you need to add just a little bit of length. So in the previous video, when I showed an overlay in Altium Designer, it was just a little bit of a nudge like this. And that was just enough to bring the lengths of these two traces to the same length, so that way the two signals line up in time. And then you can properly cancel out the noise, and you can properly read out the signal level over this entire unit interval. Now, sometimes the length matching is a bit more, that you need to enforce is a bit more extreme. So maybe you don't have one of these little bumps here. Sometimes what you'll see is you'll actually see this kind of series of bumps like this. So this is sometimes called serpentine routing. There are a bunch of different names for these different types of structures, but this is the most common one, which is just serpentine routing. Sometimes you can actually get a little bit more interesting with your length matching, and what you'll see is something that looks like this. So it looks like this trombone structure, and this is called trombone length matching, or it's sometimes called accordion length matching. There are different names for it based on the shape of the structure that you need to enforce here. But the idea here is that you can pack this very large section of trace here on this positive side in order to make sure that you lengthen this trace enough such that these two signals now overlap in time. Then you can correctly remove all the noise from that signal. If you're using Altium Designer, or if you're using another design software, they have tools that will actually allow you to automatically add in these sections of trace length so that you can make sure that your differential pairs are properly length matched over the entire length of this interconnect. And those are accessible just in the standard routing tools. It's not like you need to buy an extra package to be able to do that. So the next thing I want to look at is sometimes what you have to do is you actually have groups of differential pairs that are being routed to a very large component. So I'll just use this as an example. So here's my other positive side, here's my negative side. Sometimes what you have to do is make sure that not only do the two sides of the trace within a pair match up and align at the same time, but also between different pairs. They also need to match up, and signals need to arrive at the same time. And so sometimes what you have to do is you have the total pair having one length, and then your second pair has a second length, L2 versus L1. So if L1 is longer than L2, then what do I have to do? Well, I can't make L1 shorter. I suppose I could, but it's actually sometimes a lot easier to just make L2 a little bit longer. And so to do that, you would actually apply length matching to both traces. And the length matching that you apply, this isn't the best drawing, but the length matching that you apply needs to be symmetric. So if you go on to like Google Images and you look up length tuning structures for PCBs or some kind of similar search query, you'll actually see a lot of really interesting images that show how this gets enforced. And we're gonna have some demo videos on the channel that show how you can actually enforce that and what that looks like on a PCB layout in your CAD tools. Hopefully this shows you why you need to length match each side of a differential pair, and sometimes why you need to length match multiple differential pairs. One of the things that's actually important to remember here that I didn't mention, make sure that when you apply those length matching structures, sometimes you need to apply different structures on different sides of a trace, and it's actually best to do this closer to the transmitting end rather than the receiving end. Remember, this receiving end needs to perfectly match up these two signals, and in order to read the difference between them so that you can properly read out the digital logic state that you need to transfer down this pair. Thanks for watching. If you liked the video, then hit that like button, hit the subscribe button, help us hack the YouTube algorithm, and go ahead and leave your comments and questions. We'll try and get to them because we've been getting a lot of comments and questions lately, and we really love your feedback. Thanks for watching, everybody, and don't forget to call your fabricator.